I'm Jason. My partners are Tao and Alex. We're doing problem 9.61 for our group project. We want to find the slope at A of this beam. The given diameter of the cable is 20 millimeters, and here's the cross-sectional area of the beam. We're also given E, which equals 200 GPa. Our virtual works, we're going to start first. Here's the beam. You want to place the virtual moment of 1 kilonewton meter at the end that you want to find the slope at, and we know that the direction of the force, the reaction force, is AY going up just by the beam. So you can solve for AY, which is 0.33 kilonewtons. We're also going to solve for the angle between the cable and the beam, which is the inverse tan of 4/3, and you get a 53.13 degree angle there. So then you're going to come down here after you solve for AY, and you can plug it in here to find the moment of the beam at any point. In this case, it's any point we're declaring as X. So AY, so you can solve for VY on the other side, which is going to be equal to AY. So the V is equal to 0.33 kilonewtons. And then we're able to solve for the moment, the virtual moment, which going clockwise is positive. We get the equation 1 minus 0.33x. And then we're going to come over here and we solve using the force equations, the x and the y. Then you go through and you'll solve for BD, which comes out to 0.417 kilonewtons to the lower left. And then we'll go over and we want to solve for real work. And here's the beam. First we're going to go through and we're going to solve using the force equations. We're going to solve and we can come out with the equation AY plus BD sine theta equals 20. Get the sum of the forces in the x, and we can get BD, AX equals BDX, which equals BD cosine theta. And then we're able to use the moment at A equation, which is given right here, moment at A, and we were able to solve for BD, which is 50 kilonewtons. And then we can go in and we can plug that back in and solve for BD and the Y, AX, and then AY. BD in this one is what we want to remember. BD in the virtual work is what we want to remember, and moment from the virtual work is also what we want to remember. And then once we solve for BD and the other forces, we can come over, and what you do is you want to switch the load on the beam over to the other side, and then you want to solve for the moment where the load was. And this is the moment of the beam at any point, which in this case it's x1 is going to be the point, but you can plug any number in for x1. And you get the moment of 20 kilonewtons times x1, and this is also what you want to remember from the real work. Then you'll come over and you want to use the given deflection equations for the virtual and the real work. These are given to you, and then you want to plug them in, and they'll add together because this is 1 times theta for each equation, so you can just add them together. And you'll get this final equation for that. And then basically from there it's plug and chug. This 1 over EI is EI of the beam, and you use the given E and I you look up in the book. You want to do an integral from 0 to L. In this case L is 3. This is your equation for the moment of the virtual work times the moment from the real work. And then you're going to add it to the given equation for the virtual work, which is the negative 0.417, which is the BD from the virtual work, the BD from the real work. This 5 is the 5 meters of the cable. That's the length of the cable divided by the area of the cable times the given E. The reason you're going to add these two deflections is because the load on the beams of virtual and real cause a deflection. And after this part of the equation, it's just plug and chug throughout, and in the end you end up getting the slope of A, which is equal to 9.91 times 10 to the negative 4th radians, and the answer is actually negative. That's why it's going down. It's going down is the slope.